the last part of the lecture, which is continuation of the previous part, is the calculation of settlement. What we have studied so far is just a calculation for the capacity of the pile. We can now calculate the load carried by pile groups, everything, but we cannot calculate the settlement. Of course, when I calculate the settlement, I don't want to calculate the settlement of one pile. I need to calculate the settlement of the group, because one pile will not work individually. If I have a group of 9 piles, one pile will not settle and the other will stay looking at him. No, they will contribute, they will help him so that he would not settle, and they will settle all together as one unit. So I have to calculate the settlement of this group. To calculate the settlement of this group, there is, of course, I can calculate it with a 3-dimensional finite element method, and it will be very accurate, but it will be very complicated. So they, in many codes, they give you approximate method for calculation. This approximate method of calculation depends on substituting the group of piles with an imaginary raft footing. What is a raft? A raft is a big isolated footing. So instead of having all of these piles, I want to put something, a footing, a raft footing at a certain level, and I will say that this will give approximately the same effect of the group of piles. They said that it depends on your type of soil. Don't copy this as clay or sand. It's not important that it is clay or sand. It is important if it is end-bearing or friction. Sand is an example of something that is friction. Clay, that is an example of something that is end-bearing. But you may have piles in sand and it is friction and end-bearing in the same time, and you may have something in clay, and so assume that this is not sand. It means that friction piles. Here it is end-bearing piles. So in case of end-bearing piles, it means that the friction is not working. All I have is all the load is transferred at the bottom. So without thinking, where will be the location of my imaginary raft? At the bottom, because all of this distance is not working. It's just a media for transferring the load to the bottom. It starts acting on the soil at this level. So at this level, I have a footing here, and it is an imaginary one. Similar for the other case, which is friction. I don't have any end bearing. It is full friction. So in this case, the load will start to be transferred to the soil from this point till the bottom. So it means that as much as I go deeper, the load is transferred to the soil. So I have to choose where will be my location with this imaginary raft. This imaginary raft will be taken at the third of the length of the pile, because of course here the soil is not as good as the soil at the bottom. Usually any soil, when you go deeper, the confining pressure increases, so it is better. The soil here is of higher quality than the soil here. So a big portion of the load will be transferred here, and a small portion of the load will be transferred here. So it is equal to as if I have a triangle, And we said that for a triangle, the CG of the triangle is at the third of this. So I can take the imaginary raft at this location, which is 2/3 of the length. So now I know the location of the imaginary raft. It is at the bottom in case of end bearing, and it is at the third bottom portion of the pile for the friction case. Suppose you don't have a case of pure end bearing or pure friction. If it is something in between, if it is 50% end bearing and 50% friction, in this case, take it at the middle. It depends on your judgment. If it is 10% end bearing and 90% friction, then I will be nearer to the frictional case rather than the end bearing case, and so on. So it depends on your engineering judgment. If it is pure end bearing, it is here. Pure friction, it is here. Anything in between is depending on your judgment for the behavior. So now, just delete everything related to the piles from these two charts, as if you only see this line and this line. You don't see the piles now. Forget everything about the piles. I have a load here and I have a load here. This load will affect, if I want to calculate the settlement of a footing, I usually tell you, calculate the compressible thickness. What is the thickness of the layer that will be affected by the load? If it is very clear to me, like here is the load, and I have here a layer of rock, and this is the compressible layer, which is sand. So I know that this is the thickness of the compressible layer. That's all. But if I don't have this line, if I don't have rock, if I have soft soil that is not soft soil, medium soil that extends to the 100 meters below, what should I do? I will just take. Now I know this is the location of my footing. What is the dimension of this footing? It is A by B. What is A by B? A by B is the circumference that includes all the piles inside. If the piles are 3 by 3, then it will be a square shape. If it is 2 by 3, it will be a rectangle in shape. So A and B may be equal, and maybe one may be more than the other. So imagine that this is 3 piles, and in the other direction it is 2 piles. So this direction is the longer direction and the other is the shorter direction. I take the shorter direction, multiply it by 2. This will give me the end of the layer that I can consider in my analysis, and it will be a very good approximation, because my load is supposed to reach below till a certain level. Below it, the stress will be less than 0.1% of the 0.1% of the load. So I can ignore what is below and use this. So if I have H, I will use it. If I don't have H, I will use it to be, I will calculate it to be twice the width of this imaginary footing. Okay, so this is H. So from here to here, this is H, or from here to there, this is H. So to calculate the settlement, this now we can refer to the refer to your lecture for the bearing capacity. We were calculating the settlement of a footing. How to calculate the settlement of the footing? We use E for the soil. This is important. So we have to know, we need to know the E of the soil, Young's modulus of the soil. We need to know the height or the width, the thickness of the compressible layer. and I need to know the load on top. I know the load on top. How can I get the load on top? Just take this load of the column, divide it by this area. You will get the stress here. But this stress is at this location. This stress, when I go deeper, this area will increase because the load will be dispersed. Take an angle of 2 to 1, 2 vertical to 1 horizontal. So as much as I go deeper and deeper, the stress will decrease. Why the stress will decrease? Because the load is constant and the area is increasing. So to calculate an approximate method, just I go to h divided by 2. If this is h, I take the middle of the layer, I calculate the stress at the middle of the layer. How to calculate this stress at the middle of the layer? The same load, but divided, instead of being divided by A and B, A by B, I will divide it by A plus h over 2 and B plus h over 2. Because h is this is the distance, h over 2. It increased a portion from the right and a portion from the left. So the total increase in this, if this is A, then this will be A plus h over 2. And so on. So I can calculate the stress here. Similarly, I can calculate the stress here. Then I will use an equation. This is exactly the same equation that we used in the lecture of the bearing capacity. If you refer to the lecture of bearing capacity, you will find even the same derivation. We said that this is not an equation just coming from heaven. No, we can just derive this equation. Start from Young's modulus of the soil, which is equal to the stress divided by the strain. What is the stress? The stress is the load divided by the area. What is the strain? It is the settlement divided by the length of the layer. Just substitute in the equation, you will end up having this equation. What is this equation? Delta H, which is the settlement. This is exactly what I need. Is P divided by A, which is the stress here at this middle layer, multiplied by 1 over ES, which is Young's modulus, multiplied by H with the full thickness of the layer. So everything here I know. I substitute here to get the settlement, so I can now calculate the settlement of any group of piles. And so on. This is the same shape, but in terms of delta sigma and P column. This is the normal shape for the equation, but this is applying the equation in case of my this case or this case. So this will be the settlement of the pile. This is an example. If you see this example, this is, it's not written, but this is a friction pile. So my imaginary footing will be in the third, in the middle part, or the lower third of the pile length. This will be my imaginary footing. And this is the total from here to the bottom. It is 10 meters. So I will go at the middle portion of it, and I will calculate the stress here, and this stress will be the stress that I require, and I will just use my equation, my normal equation, direct substitution. I get 2.9 centimeter, so the settlement of the group will be this value. I just want to go very quickly what is the capacity of pile groups under vertical tension load. As we said before, a tension load is what is the difference between, of course these are portions of the code for the design of this tension case. what is the difference between the tension and the compression? We said that we have, in normal cases, in single piles, we have, we said that the friction will work, but the end bearing will not work. And we said that we are going to add to this friction the own weight of the pile. Here, it's not the own weight of the pile, because I'm speaking now about a pile group. In this case, I have a pile, and I have in between soil. And it's not only the soil in between. There may be soil outside that will cling or attach itself to the piles and will be additional load on the pile. So what I have to do, imagine that you have a plant in the ground and you try to get this plant out of the ground. Of course, the root of the plant is below the ground. When you try to push it outside, sometimes you find that the roots are coming with part of the soil attached to it. Does this happen with you? Did this happen with you before? Trying to imagine that you have something in the ground, a small plant in the ground, you try to pull it. In some cases, in most cases, you will find soil attached to this. So when you were pulling it, actually you were feeling the weight of the plant and the weight of the soil that is attached to it. This is exactly what we need to do here. We need to take part of the soil with us. How come? I need here a drawing. Take this drawing. Imagine that this pile or this group of pile, instead of having a vertical load below, I'm having a vertical load up. It's a tensile load. This tensile load will take these piles outside. Everything, all the soil in between will be included. This is okay. I know that because piles are surrounding the soil, so they will take part of the soil, this soil with them. But actually, would you expect the soil here to just to leave the pile go, or will be attached to it? It will be attached to it. So the method depends on saying that from this point, take an inclined line that is has an angle of 4 to 1. 4 vertically and 1 horizontal. So take a line like this with a slope 4 to 1, and from the other side another line 4 to 1, and everything in between will be included in the amount of load that will be carried by the pile. So you have here to calculate two things: the summation of the frictional forces of each pile. This you can calculate based on your previous, what is the load that will be carried by a single pile. Multiply it by the number of piles, then this is what we can, the maximum that the group can carry. And calculate another thing. What is this another thing? That instead of the piles being attached to the soil, no, the pile and the soil were detached from the full mass. So in this case, I will have to calculate the weight of a block. What is the shape of this block? This is the bottom of the block. This is the side of the block inclining 4 to 1. This is the other side of the block inclining 4 to 1. And all what is inside is soil. I don't have any concrete. Ignore any concrete that you have inside. It is only soil. So these are the two cases that you have to calculate. The first case, calculate a single pile, the capacity of single pile in tension multiplied by the number of piles. This is the tension, the tensile capacity of the group. But this is one case. The other case is that the tensile capacity is not going to work because the soil and the piles will be detached from the soil mass. So in this case, I will take a shape. It's a wedge. This wedge has the following shape. This is the bottom of the wedge. It's a trapezium. and here it is inclined 4:1, and here it is inclined also 4:1. Calculate the area, calculate the volume, multiply it by the own weight, by the unit weight of the soil. This will give you the counterweight that can be carried by the pile group. Check which one is smaller. This one will be the portion that will be carried. This is exactly what is written here. This is 4:1, which is we said that we have to calculate two cases. The first case is the summation of the tensile force of each one, and the next one is the wedge, the own weight of the wedge. Lateral resistance of pile groups. This is something related to the lateral resistance of the piles. Do you consider, if you have a group like this, and I have a lateral load in this direction, will all piles carry the same lateral load? There will be a difference. What is this difference? The piles in the front will carry the whole amount. Imagine that you and your friends in the imagine, as we said, imagine you and your friend are, you know, the pulling the rope. There is a game where a group of two groups, and they are pulling a rope, and we try to see which group will pull the other. Usually the person in the front is carrying all the amount of the load. That's why they usually choose the strongest one to be in the front. So if you are in a line, usually the person in the front carries the major task. Here also, I am pushing this group, and these 1, 2, 3, 4 piles are in the front. So these piles in the front are faced by the soil, so they carry the major amount of load. What about these piles at the sides? They carry also a load. Why? By friction, because they want to move in this direction, and the soil here is preventing them from motion, so they carry also part of the load. And here the same. What about these? These piles are hidden in between. They don't face the soil in front, and they don't have friction with the soil at the sides. So they move with the group. If the group moves in this direction, they will move with them. If they stop, they will stop. Their contribution is very minor. Their contribution may be structural, depending on their rigidity, but the soil is not affecting them, because this soil was affected by this. If these two piles move in front, then this soil is loose now. It cannot carry anything, and similarly all of the amount here of this soil. So if I take this group of piles, then these two piles, they have the number 1, they carry the most of the load. Why? Because they are in the front, so they can carry load by bearing, and they are at the side, so they can carry load by friction. So these are the biggest contributors. Piles number 2, the second contributors. Why? Because they can carry the load from the soil by the soil in the front, but they don't have friction with the sides. So they are less than number 1, but they are more than all of the others. Then I have number 3. They can carry load by friction only. They cannot carry load by bearing. So number 3 here and number 3 here is the third group. Number 4 is the least group, that they can carry minimum load. Something called negative skin friction. What is negative skin friction? To go to the negative skin friction, I have to see this photo. 2 persons dancing together. If suddenly one of them have problem with his legs, what will happen? instead of, imagine that this person is more or less carrying the girl in front of him. If he suddenly have a cramp in his leg, what will happen? He will fall. Unless she is strong to carry him, he may not fall. But if he is not strong, then the opposite has happened. Instead of him carrying her, it will be her carrying him, and they may fall together. This is exactly what is happening here. This is soil. And the soil is supposed to carry the pile. But if I have soil that is very, very soft, that will consolidate with time. So what will happen? Under own weight, it will consolidate. It will start settling down by own weight. So what will happen? I will put my pile here. The soil will get attached to the pile, and it will stay like this. It is now carrying the pile. But 1 month later, the soil starts to consolidate, so it settles down. So when it settles down, it starts to transfer negative load on the pile. So instead of carrying the pile, it is being carried by the pile. This is the problem, because in this case, if you design a pile that has a negative skin friction carried by the pile, suppose that this pile, I tell you that this pile will carry 100 tons. 80 tons for friction, or 60 tons for friction, and 40 tons for end bearing. Later, after 1 month, this 60 ton of friction will be transferred to be 60 tons as a negative load on the pile. It's the opposite. So this pile will only carry 40 tons. It can carry 40 tons. But what is the load carried by the soil? The negative load of the soil alone, it is 60 tons. So the pile will fail under own weight. I did not discuss here. It was supposed to carry 100. This 100, 60 here and 40 here. Later, when this consolidates, this 60 will be added to the 100. So I will have a load of 100 plus 60. So it is 160 carried by 40 tons. Fully settled. It's a complete failure. So this is a big problem. The bigger problem is what? The bigger problem is to have a small layer here that you will ignore. Or will say, I will have a very small layer here that instead of having this layer with a thickness of H, no, it is just H over 20. Small minor layer. And in top of it, very good sand. So I will design this very good sand as carrying the pile. But actually this very good sand is being carried by a very soft soil. So this soft soil with time, it will settle. Once it settles, this load will also be carried by this layer. It will, this small layer will settle, carrying all what is above on top of it, down. So it will change everything. So this is very important that you conduct a very good site investigation to see all layers, because if you have a minor layer that is soft clay, even if it is followed by stronger layers, this soft clay will change all that is above to be negative skin friction. So this is very, very important, and it can, as I gave you an example, the load can be completely changed, and the case may be changed from safe to severely unsafe, and the pile will fail. Last thing is the quality control. You remember I told you that I have pile load tests. And this pile load test I can conduct it on selected piles. If it is destructive, I will load it to failure. If it is not destructive, it is a working pile, I will just load it to the working load, and that's all, or maybe more than the working load, say 1.5 the working load, and that's all. But I want to test all of the piles. It is not enough. I cannot just depend on a pile that I don't know what it is doing. When I have a problem with my stomach, I go to the physician and he tell me to do an ultrasound, something like a sonar that you all know. What is this ultrasound? Ultrasound is a test. They put something on my belly, and they just a wave will penetrate, and the wave will come back again. They analyze this wave and tell me what is inside. We do the same for the piles. We put a wave on top here, and this wave will go down and will be reflected up, and I will collect it again. Once I collect it again, I analyze it to know. I know the depth of the pile from the velocity of the wave going up and down. So this is one thing very important. I know the material of the pile, because if the material was changed, the velocity will change. So everything is related to the velocity of the wave that is reflected. So what I can find from here, I can find if there is an inclusion. During construction, something fall. Maybe somebody dropped something in the pile. It's a problem because it will affect the pile. So if there is something inside, if there is a crack that happened, if there is joints, suppose that they are constructing a pile and then suddenly something happened, everyone left the site and then they came again and continue. There will be a separation between what was constructed many hours ago. You may have here a layer that is very soft, so the pile will be bulging outside. Of course, this is not a big problem if there is a bulging outside, but you need to know that there is a bulging outside, because you just increase the diameter of the pile. But the opposite is not good, because if soil just collapsed on the pile, then the diameter of the pile will be reduced. It can also describe the soil around the pile with more sophisticated equipment. He can tell me this equipment can tell me. It can tell me the stratification of the soil that the pile is penetrating. It can tell me that if there is a material change. Suppose I started casting the pile, and then I got short of material, and then I brought another material from another concrete from another pump, and it was different. It was not good. Then this test can tell me that here you have a difference in the where. In the material lab, yes, this is correct. So you can do this test on site, and you can do it on all the piles, so you will be sure of the depth, cross section, material, cracks, anything that is inside the pile, so we can check. So now we can check the load of the pile by testing, and the shape and the dimensions and the material of the pile. So now I can be sure of the pile in all way. This ends our all of the lectures for the piles, and thank you for your patience, and see you next lecture. Thank you.